Let's talk about nuclear decay particles. Before we discuss that, I would like to talk about the symbols of elements and particles. Now, typically, the symbol of an element is a letter that is capital or a letter that is capital followed by a letter that is not capitalized. If you see a letter with a number in the top left, that is typically known as the mass number. Of that particular isotope, you would say. The mass number is the number of protons plus the number of neutrons. But typically, you should say that that is the number of nucleons. Which is the number of particles that would be found in a nucleus. And the things that are found in the nucleus are a proton and a neutron. So for the purposes of this video, I'll be referring to that as the number of nucleons, either protons or neutrons or protons plus neutrons, things that are found in the nucleus. Now, if you see a number on the bottom left, that is typically the atomic number for isotopes. And the atomic number is the number of protons. But for the purpose of this video, I'm going to be saying that is the number of positive charges. The number of positive charges. Now, protons are positively charged, but as you will see in this video, they are not the only thing that is positively charged. We can have other things that are positively charged. Now let's quickly talk about nuclear particles, okay? So lowercase n as opposed to uppercase n. Uppercase n is nitrogen, and lowercase n is neutron, okay? So a neutron has zero, so I would put a zero down left. It would be a zero positive particle. So neutrons are not positively charged. They are neutrally charged. They have no charge. So they would have no positive particle. They're not a positive particle. So I would put a zero down on the left. But they are found in the nucleus. So in the top left, I would say that it is a 1 for a number of nucleons. So you have one neutron that would be found in the nucleus. Now, on the other hand, if I had, say, an electron, so electron with the E, okay, I would put a -1 downstairs on the bottom left because not only is it not positively charged, but electrons carry a negative charge. So I would put that negative charge in the bottom left. And in the top left, I would put a 0 because electrons are not found in the nucleus. They are found in the electron cloud. Now let's look at the chart that's called nuclear decay particles. There are about 6 main nuclear decay particles. You'll see that the bottom one is similar to a previous one. The 3 main ones I'm going to discuss right now are alpha, beta, and gamma. Okay, so alpha, beta, and gamma that's Greek alphabet, alpha, A, B, C. So in the Greek alphabet, that's A, B, C, the first 3 letters of the Greek alphabet. And they're named that because that's how they were discovered. They were discovered first alpha, then the beta, then the gamma. Alpha particles are really highly charged, lots of energy helium nucleuses. And they go by multiple symbols, okay? That right there, A, that's an alpha, okay? Or you can have an alpha with a 2 down here, which means it has 2 nucleons. That would be 2 protons. And then a 4 up here being I'm sorry, 2 down here for the 2 positive charges and a 4 up here for the 4 nucleons. So 2 positive charges, that's 2 protons, and then it has 2 more neutrons. So 4 nucleons, 2 of them protons, 2 of them neutrons. Alpha particles are famous from the Rutherford gold foil experiment, which you may remember from atomic theory. What type of decay does it occur in? It occurs in alpha decay. Okay. Here's an example of a equation, nuclear equation involving alpha decay. So you have radium-226, so this would be radium with 88 protons and 226 total nucleons, or the mass number of 226. And that decays into radon, which has an atomic number of 86, or 86 protons, and 222 neutrons and protons, nucleons. Okay. And the decay is the alpha particle. So you'll see that nuclear equations typically, not all of them, but typically work like this, where you call this the parent isotope, and it decays into the daughter isotope, and it will give off a nuclear decay particle and lots of energy. So you would say this is radium-226 that decays into radon-222 and releases an alpha particle during alpha decay. That's how you would say what has happened here. Beta particles are high energy, high speed electrons, or it could be positrons. Okay. The general nomenclature is that it's a B, or the symbol is a beta, I should say. If we're talking about a high energy electron, that would be a beta negative, really. And a positron, and we'll talk about what a positron is in a second, but a positron would be a beta positive. The symbol for a beta negative or a high energy electron, high speed electron, is here. We discussed this previous. The E with the -1, because it's not providing a positive charge, it's only providing negative charge. And a 0 because it's not in the nucleus. No, 0 nucleons. A positron would be a positively charged electron, it has a positive charge. Sometimes the particles can be captured, which we'll talk about that in a second. Okay. So a beta decay would be something like this right here. So beta decay, so lithium has 3 atomic number, 8 is the mass number. So lithium 8 decays into beryllium 8 and gives off a beta negative or particle. So this would be a beta negative decay. Over here we have thorium-232. That's the parent isotope. It decays, and the daughter isotope would be actinium-232, and the particle that would be given off would be a beta positive particle. Now notice that the numbers add up. So here this is 3, and then on the right side of the arrow, it's like an equal sign. 4 plus -1 would be 3. And then on top, this is an 8. 8 plus 0 is 8. And then over here, 232 is 0 plus 232. 90 is equal to arrow. +1 plus 89 is 90. And up here is the same way. 88 equals 86 plus 2. 226 equals 222 plus 4. Now, sometimes beta decay is not a decay where you see the particle on the right, but a capture where you see the particle on the left. So this is a electron capture. It might be called a beta capture or a beta negative capture. So this is potassium-40, beta capture, and it goes to argon-40. Now this is still the parent isotope, and this is the daughter isotope, but this time it's a capture. The particle is coming into and hitting this isotope. So notice once again, 40 plus 0 is 40. 19 plus -1 is 18. Now, gamma rays are not really particles. Okay, they are penetrating electromagnetic radiation. This is the symbol of a gamma. Okay, atomic bombs release a lot of gamma radiation. That's the very destructive part of it. So gamma decay will look like nothing happened. So this is technetium 99, and it decays in the technetium 99, but it gave off energy. So there's a little bit of a change inside the nucleus that can't be seen in this nuclear equation, but basically you start with the same isotope and end with the same isotope, but its rearrangement has released energy, and that energy is gamma radiation. Notice gamma radiation is 0, 0, meaning there's no positive particles and there's no nucleons involved. Positron decay, we kind of went over a little bit. The positrons are beta positive particles. It's hard to see there, but it's beta positive. And a positron is a positively charged electron. It's positive charge, but it's not in the nucleus. Positrons are used a lot in PET scans, if you've heard about those in medicine. And they're involved in beta decay. And here's an example of a beta decay. So thorium-232 beta decays into actinium-232. Notice once again, 90 equals, that arrow's like an equals, 1 plus 89, and 232 equals 0 plus 232. And then you just have your typical subatomic particles that can be released during nuclear decay. So protons, neutrons, electrons. Protons are positively charged. They are said to have a mass of 1 atomic mass unit. Neutrons are the same mass, but they do not have the same charge. Electrons are 1/2000th the mass, okay, and they have a negative charge. So here's the symbol of a proton that you may find. Here's symbols for neutrons that you may find, and here's symbols for electrons that you may find, okay. Proton emission is not something we study at our level, so we're not going to worry about those kind of equations. Electron emission is what we discussed in beta particles. But a neutron is what is used in fission and fusion. Okay, so let's talk a second about fission and fusion. Fission means that the isotope splits apart into smaller isotopes. That's typically what's used in nuclear power and nuclear bombs. And fusion is when isotopes combine, and that's like element builders. That's what's happening inside of stars that builds elements. Fusion is also used to make man-made elements, the bigger ones. So let's look at this first fission. So uranium-235, that's atomic number 92, mass number 235, 92 protons, 235 protons plus neutrons. When it gets hit with a neutron, so in a nuclear reactor, they fire neutrons at these uranium-235, and it will break into parts molybdenum 95 and tin 139. So in this case, this particular reaction, this uranium will break into two things. Okay. Now in the process, it will release two neutrons. So let's look at the math on this real quick. So 235 plus 1 is 236 equals 95 plus 139. So that's 234 plus 2 times 1 is 236. So that coefficient gets multiplied. So that there's 2 on top over here. So 95 plus 139 plus 2. So the 236 on the right side. And then on the bottom, it's 92 plus 0 equals 42 plus 50 plus 0, 2 times 0. So that's 50 plus 42 is 92. Now in fission, you're combining them. So you will see two isotopes over here, and it makes one isotope on the right plus a particle, typically neutrons, okay? So I have hydrogen 2 and hydrogen 2 will combine and fuse, come together to make helium 3. So let's check the math. 2 plus 2 equals 3 plus 1. 1 plus 1 equals 2 plus 0. So I hope this chart helps you out. I hope that this video helps you out. And good luck.